Hello everyone, it's been a while. So today, I'd like to address some questions and provide some answers. These are issues I've frequently encountered while developing products recently. First, let's take a look at a case study for today, which we'll delve into shortly. The question is, how is this model created? How is a power bank like this one made? We'll tackle that later on. First, let's clarify a specific issue. Look at this surface in the center of the view. This surface here in the center. It's a hyperbolic, a double curvature shape, right? It's a double curved surface. But here's a problem I recently discovered when trying to build this. Using the curves workbench, the resulting surface may not achieve the desired quality. Specifically, the golden surface tool sometimes cannot produce this result. I'll explain this in detail. What's the reason for this? Alright everyone, let's examine this. Here is the surface generated using the golden surface tool to fit the curves. I believe many users have encountered this to some degree. You want to create a double curved shape like this, and furthermore, after mirroring it, you want axis symmetry in G1 continuity at the common tangent line along the axis of symmetry. But clearly, using this approach, it's very difficult to satisfy that condition. For example, if we mirror it now, as we can see in this project case, I applied G1 continuity constraints to both this side and the other side, along the common tangent direction. However, there is still noticeable pinching on both sides here. The issue is that in the region of the four corner points, the curvature connection is not uniform. So when we use the curves workbenches, surface fitting tools, achieving this effect is very difficult. This kind of effect, for the specifics, you could try it yourself later after the video ends. You can give it a try. So the core problem with it is that if you take its four boundary curves as guides, and you need to add multiple control curves and curves. Normally, it only allows one control curve along each direction, one for the X direction and one for the Y direction. If you add too many control curves, and each of these curves is constrained to be tangent to its axis direction. Specifically, when there is this kind of tangency, G1 continuity condition, the algorithm cannot correctly determine which curve corresponds to symmetry about which axis, so it fails to generate the surface. In many cases, when you add a large number of such control curves, whether they are in the X or Y direction, the software will simply report a dimension or constraint error. So that's the fundamental issue here. This is currently a limitation of FreeCAD. So if we want to achieve our desired double curve shape, to create a smooth hyperbolic shape like this one, as we mentioned in a previous tutorial, in that very early video, I demonstrated this starting from version 0.18. That is in the Sketcher workbench. If you want to constrain a B-spline, right? To constrain a B-spline, you need to manually add straight lines. And these straight lines are construction geometry, virtual lines, right? Back then, to satisfy the G1 continuity condition, the tangency condition between a straight line and a spline was quite tricky. As my longtime viewers know, you need to delete its equality constraint. Furthermore, you cannot modify its weight. Its setting condition is to select a point on one of its splines, and then select a straight line. Then you remove one of its equality constraints. Only then can you achieve such a constraint condition, right? Then with version 1.0, with a major 1.0 release, it gradually added support for direct tangency between splines and straight segments. But sometimes it still reports an error. It reports a constraint redundancy, redundant constraints. In some of my earlier videos, I discussed one method to achieve this kind of double curvature shape. That's the first method. The first method is to go into the Sketcher and draw a cross-section for the sweep. Let's call it D. Let's assume it's D. Then, as the second step we need its overall sweep path. We'll call it P. Right, call. So in other words, what does D represent? D is essentially the profile that needs to be swept. This ensures that along your sweep path, the entire curved section, this curved part maintains continuous curvature. and it must be tangent to the straight segment, so that when you sweep it, the result is a complete, seamless shape, right? The advantage of this approach is that the cross-section, the profile you define, will be perfectly smooth. So that's one method. Today, let's try the second method. You can see it's perfectly tangent here, correct? It is perfectly tangent, and we can see this area is actually a blend surface that gradually disappears, right? That is, starting from this location here, and then it begins to fade out as it reaches this point, making it a vanishing surface. It completely disappears into this area. Let's take a look in Blender, but let's check its condition inside FreeCAD. Looking at the overall zebra stripes, you can see it's continuous here, right? This means from this point down to here, within the shared region. Using this location as our reference cross-sectional plane, this area is guaranteed to have G1 continuity. Isn't that right? Then, moving further down, starting at the second interface. As we reach this interface, it starts again. There's a certain change in curvature, and we can see the zebra pattern. Also confirms that the curvature connection in this area is perfectly fine. All right, next let's talk about how this entire case model was actually built. We'll create a new one here, a fresh file. Then, we'll focus on today's key topic, which is how to ensure that your cross-sectional plane maintains axis symmetry. Because FreeCAD's native workbenches do not support this functionality. Axis-aligned tangency, whether in the 2-axis direction, Y or X, or even in a 3-axis direction relative to a section plane. This kind of tangency in all directions, right? It doesn't support axis symmetry, nor does it support axis-aligned tangency. So, we need to find another method to achieve this condition. This condition means we need to draw a cross-sectional plane like this one. Right, draw such a cross-sectional plane, and then ensure it is tangent along the y-axis here, and along the x-axis direction at this location. Apply a tangency constraint in a virtual direction. Specifically here, we need to draw a virtual line. For this part, we will draw a virtual line as a substitute. We'll make the x from here and the y from here tangential to each other, right? Therefore, here we'll draw a spline. Alright, after drawing the spline, we'll snap to its endpoints on both sides and draw 2 straight lines. These 2 straight lines are then converted into auxiliary lines. Next, we apply a tangency constraint between this spline and the auxiliary line. At this point, we'll see an error reported below, indicating that tangency is not supported. Tangency, right? Unsupported tangency. This kind of error is actually quite common. Tangency via point constraint is specifically for Bezier curves. So when we encounter this, we'll use a weight point on this Bezier curve to make it tangent to the line. The same applies here. If direct tangency between the lines is not possible, we'll use a weight point on the spline to maintain tangency. Also, can we make this part horizontal? We'll just draw it as is. Alright, the next step is to create a cross-section plane. Use an external geometry projection to project one of its endpoints onto it. Here, we have created the cross-section. Next, we use the sweep tool and use this sketch as the profile. Then select the sweep path. Alright, done. Then we uncheck the solid option. Now, looking at the sweep result here, it extends beyond the boundary, right? Because the profile is placed too close to the sweep path, causing the generated surface to overshoot here. So here let's pull the cross-sectional plane of this sweep outward. Good. Now after pulling it out, we can see that, this area here looks correct. Next, we'll use the tool inside the curve's workbench, inside the surfaces menu, the boundary surface, to fill in this entire boundary region. After it's filled, we click OK. Now let's take a look at the overall result. In shaded mode, it appears completely fine. Right, there are no issues. Alright, next, let's select all these objects and join them. Once joined, let's try directly mirroring it to see if it can achieve G1 continuity with the lower section along the z-axis. So here, we use the mirror command to mirror the top half to the bottom. Now, let's examine the overall shaded view. It looks perfect, a completely seamless connection. Look at this area along their shared boundary line. Both surface A and surface B here are perfectly tangent to this central axis. Tangent to the axis. So that's the first method, right? That's method one. Now, as I mentioned earlier, the older method, the traditional approach, works because the entire connection between surface A and B is just this single line, which is a shared curve. The connecting area for A and B is this shared curve. And since we already defined back in the sketch, G1 continuity for it in both the X and Y directions, when we simply mirror it over, the continuity quality on both sides remains G1. The second old method, also mentioned in a previous video, involves directly sketching the entire cross-section as one complete profile. Then, we'll have this entire cross-section revolve around a spline like this in a full 360-degree sweep, which can achieve the same effect. The key difference between the two methods, however, is that the cross-section here achieves G2 continuity, or can even be set to a higher continuity level like G3. With this method, the continuity level achievable here is limited to G1 because the sketcher can only enforce G1 constraints. That's the sketcher's limitation. All right, now let's look at this area. Specifically this part. How do we connect a curve here? Because the faces here are quite fragmented, we can't create a clean loft directly across them. Right, there are actually many. Yes, there are many of these. Small, broken boundary surfaces here. So, a direct loft would look very messy and uneven. First, let's create a spline. But before that, let's combine these, then extrude them, making sure the extrusion passes through both sides. Next, we'll remove this section. After removal, we can see there are actually a lot of fragmented faces here and here. Look at these areas where the edges are discontinuous. Here and here. These are all broken edges. Therefore, if we try to bridge a curve directly across this, connecting like this, it obviously won't work. So, here we'll use a method where we extract these curves. First, let's extract part of this curve. We only need half because the overall shape is relatively symmetrical and regular. So we'll simply join these curves and do the same on this side. They're also joined into a curve, and then now we can see that the contours on both sides have been successfully created for us. Once it's created, you can directly perform a loft operation on it. We only need to loft half of it, and we can simply mirror the other half later. Then, click Loft and loft it directly. Lofting it directly here is one way. We could also use other methods. What method? That is, within the curves workbench, we can manually, right here, we can manually add a control curve to manage the curvature change at both ends. Alternatively, we can use a blend curve to create a spline based on its original trajectory. Then, creating a four-sided surface mesh is also an option. That would work fine too. For now, I like to just mirror this surface. Then, on the other side, we'll have it ready. Next, we'll combine these shapes again. After combining them, we can see that this loft source here also needs special attention. A key point to note about it is that people often find they can't loft due to a certain gap tolerance being present. Now, let's create a hole here. Let's assume we want a round hole, right here. The current boundary is quite complex, right? There are fragmented surfaces everywhere. So, the section it cuts out will also have many small patches. Next, we separate this extrusion. After separation, we can see this side, this side, this side. The whole circle is split into 4 segments, right? The entire circle is divided into 4 sides. A complete circle is periodic, correct? But here, these fragmented surfaces break it into 4 sides. Or more accurately, an insided face, right? If you try to loft an insided face with your sketch circle, in most cases, it won't work. Why is that? Because a complete sketch circle is a full, closed periodic curve. But the circular edge created after cutting the solid might be an insided face. This mismatch in topology makes it impossible to loft directly. Let me give you an example. Let's refer back to this area here. Yes, this area here. Let's draw a circle like this, draw this circle, and see if we can adjust its position. Now we're going to attempt to loft and combine these sections. Right? There are a few approaches we could try. The first method is to take these fragmented faces, or rather their edges, and use the Join Curve tool. Yes, join them into a single curve. After joining, we can then attempt the loft operation. Let's try it. Looks like that works. It works here, but sometimes it won't. Yes, sometimes it just fails. For instance, the loft we just created here. These areas are a bit twisted, right? That's because it's a force connection. 5 edges are being forcibly merged into one. So for a more reliable result, we suggest a different method. What method do we use? We switch to the part workbench and create a copy of the original boundary edges from this loop. Sometimes the previous method fails. Like with the curves workbench we used earlier, it can fail, sometimes due to slight deviations between the geometries. So even if it appears to join initially, the connection isn't robust. Later, when you try to build surfaces from it, gaps can still appear. That's why we directly extract a copy of the original shape. Let's combine it. And then with this section here, we have this connect 002 here. And then with this sketch here, let's connect them. All right, now we can see the original boundary curve. Over on our side, it's been broken up by these fragmented faces into an insided shape, right? So the overall loft operation for it will proceed downwards in this insided form. This way, the result of the loft will correspond correctly, with the original loop at the bottom, preventing any mismatch errors. So let's try using that same method from before again. We'll use the exact same approach and give another go. The method I just mentioned, we'll use this join curve to loft it, and immediately we see it's throwing an error here. It's not supported. This method isn't supported here. Alternatively, if we try using the lofted surface tool inside the surface workbench to loft it, the result it generates looks odd. That doesn't work either. Even if it did work, during the subsequent process of stitching these surfaces together, we'd still run into issues. Extracting its original boundary curve and lofting that is the way to avoid mismatch contacts, which would otherwise cause shape inaccuracies. That's the situation. All right, over here, let's simply fill it directly, and then create a solid from the whole shape. And I see that the solid created here appears green. Now, if we had used my earlier method, where you fit all those fragmented edges into one single edge, and lofted it with the sketch boundary, the result might not have been a valid solid, not a proper solid. It could have just been a shell. And that concludes today's discussion on creating a double curved shape. This explanation of the modeling process, and how to achieve something like tangency to the axis, in order to create such a curved surface shape. Alright, thank you for watching.